The floor beneath you is accelerating, right now, upward, through curved spacetime. And the sensation you have always called gravity, that familiar downward weight pressing you into your chair tonight, is not the earth pulling you at all. It is the floor pushing you away from the path the universe is trying to put you on. 300 years of physics class told you gravity is a force. Einstein said it isn't. And every GPS satellite quietly overhead right now is running a correction that only exists because he was right. So what exactly is holding you in your chair? That's the question we answer tonight. Stay with me, because this one will melt your brain. If you are new here, welcome to Sundown Science. Subscribe and make yourself comfortable. We are about to take apart everything you think you know about gravity and replace this force you have felt every second of your life with something stranger, older, and yet still not fully explained. Now, settle in and let's ease into this one slowly. Part 1. The thing you think you understand isn't real. Right now, in this moment, you are being lied to by your own body, not maliciously, not because anyone designed it that way, but because the human nervous system, shaped over millions of years of evolution on a single planet with a single gravitational environment, has had no reason to develop the ability to perceive physical reality accurately at the level where reality actually operates. Your brain is an extraordinarily efficient prediction machine, and it has spent your entire life constructing a model of the world that is useful enough to keep you alive, fed, and functional. It is not, however, entirely correct. And nowhere is that gap between your experience of the world and the actual mechanics of the world more dramatic, more disorienting, and, once you fully sit with it, more genuinely unsettling than the place where gravity lives. You have known about gravity your entire life. You learnt its name before you could read. You felt it before you could walk. You have never once, not for a single second of your existence on this planet, existed outside its influence. It is the most familiar phenomenon in your entire experiential universe. And that familiarity is precisely the problem. Because the thing you think you understand when you think you understand gravity, the invisible pulling force, the reach of the earth from its center to your body, the thing that makes apples fall and keeps the moon in its orbit and holds the oceans to the surface, that thing is not real. Or at least, it is not what you think it is. The force you have believed in your entire life, the one they taught you about in school, the one that feels so self-evidently true every time you stand up and feel your weight pressing down through your feet, that is not the mechanism, that is the performance. And the actual machinery underneath it is something so strange, so geometrically alien to human intuition, that even physicists who work with it every single day will tell you that they never fully stop finding it bizarre. So let's begin at the beginning. Let's begin with the lie, because you need to understand exactly how convincing it is before you can understand what replacing it actually means. Gravity, as most people understand it, is a force, a pull. The Earth has mass, and mass creates a gravitational field, and that field pulls on every other object with mass, drawing things toward the center of the Earth with a strength that depends on how much mass is involved and how far apart things are. This is the Newtonian picture, named after Isaac Newton, and it is an extraordinarily powerful one. Newton published his law of universal gravitation in 1687 in a work called the Principia Mathematica, and what he gave the world was something genuinely revolutionary. For the first time in human history, a single mathematical framework could explain both why apples fall off trees and why the moon stays in orbit. It could predict the motion of the planets. It could calculate the trajectory of a cannonball. It could, if you were patient enough with the arithmetic, tell you where Jupiter would be in the sky 100 years from today. It unified the physics of the sky with the physics of the ground, and for 228 years, from 1687 until 1915, it was the best description of gravity that humanity possessed. And here is the thing that makes unlearning it so difficult. It works. For almost every situation a human being is likely to encounter in daily life, Newtonian gravity is so accurate, so precisely predictive, that using it gives you answers indistinguishable from the truth. Engineers use it to design bridges. NASA used it to send spacecraft to the outer solar system. Artillery calculations use it. Orbital mechanics textbooks use it as the primary framework. It is so good at predicting outcomes that even today, when we know it is not the complete picture, we keep using it because for most practical purposes, it is good enough. And that is actually one of the central cognitive traps in understanding gravity. When a model works this well, when it has this kind of predictive power, when it matches your everyday experience this completely, your brain files it under true, not useful approximation, not good enough model for human scale physics. True, real, the thing itself. So you grow up with this picture. The Earth pulls you down. Gravity is a force. Down exists because the Earth is there. And then you go to school and they confirm it. They give you the equation. Force equals the gravitational constant times mass 1 times mass 2 divided by the distance squared. They show you diagrams with arrows pointing toward planetary centers. They might even do the experiment where you drop two objects of different weight and they hit the ground at the same time, and you nod, because this all fits perfectly with your experience of reality. Of course, gravity is a force. You can feel it. You feel heavier when you carry a backpack. You feel lighter when you jump. The sensation is real, and the sensation matches the explanation. So the explanation must be real too. This is where the psychology gets interesting, because the sensation of weight, the thing you feel pressing you into your chair right now, is real. The pressure in your joints, the compression in your spine, the way gravity seems to be reaching up through the floor and insisting on your existence in a specific downward direction, all of that is a genuine physical experience. But here is what your body is not telling you. That sensation is not gravity. That sensation is something else entirely. And the moment you understand what it actually is, the entire conceptual architecture of the universe rearranges itself in a way that you will not be able to fully undo. Your experience will keep telling you the old story, but you will know it is not the complete picture. What Newton could not explain, and what he himself freely acknowledged, somewhat to his frustration, was what gravity actually was. How did the Earth reach out across empty space and grab the moon? What was the mechanism? Force requires contact, or at minimum, some kind of field propagation, and Newton had no explanation for how gravitational influence transmitted itself through the void between objects. He described what gravity did with incredible precision. He had no idea what it was. He even wrote, famously, "I feign no hypotheses," meaning he was making no claim about the underlying mechanism, only about the mathematical relationships. For over 2 centuries, that was good enough, because the predictions were so accurate. The machinery could stay a mystery. The model worked. And then, in 1915, a German-born physicist named Albert Einstein published a paper that did not merely refine Newton's picture, it replaced it. Not because Newton was wrong in the sense of being inaccurate, but because Einstein found the machinery. He found what gravity actually is, at the level of mechanism, not just description. And what he found was not a force. It was not a field in the way anyone had imagined. It was not even a pull. It was the shape of space and time itself. That sentence might feel abstract right now. You might be reading it and thinking, yes, space is curved, I have heard that, sure, okay. But I want you to hold off on filing that under understood too quickly, because the full implication of what Einstein discovered is not something you can absorb in a sentence. It takes a slow demolition of everything you think you know, which is exactly what we are here to do. Because right now, in this moment, the floor beneath you is not keeping you from falling by holding you up against a downward pull. It is doing something far stranger. something that involves the four-dimensional geometry of reality itself. And we are going to take it apart piece by piece until you see exactly what that means. Let's start with the chair problem, because that is where it gets personal. You are sitting, presumably, or lying down, or standing as you engage with this. You are in contact with something solid, a chair, a floor, a couch. And from the Newtonian perspective, here is what is happening. The earth is pulling you downward with a gravitational force, and the chair or floor is resisting that pull with an equal and opposite normal force. And the two balance out, and you remain stationary. That is the classical picture. Comfortable, intuitive, completely at odds with general relativity. Here is what Einstein's framework says is actually happening. You are not being pulled down. You are trying to follow a path through spacetime, a curved, four-dimensional path called a geodesic, and the path you would naturally follow, the path that requires no force whatsoever to maintain, is what we call free fall. Falling is not an unnatural, forced state that gravity imposes on you. Falling is the default. Falling is what happens when nothing interferes with your motion through curved spacetime. The apple does not get pulled off the tree, the apple gets released. And the moment it is released from the branch, it stops being pushed and starts doing what objects in curved spacetime naturally do, which is follow the curvature. And following that curvature, from our perspective here on the surface of the Earth, looks exactly like falling. Right now, you are not falling. And that is because something is actively interfering with your natural motion through spacetime. The floor, the chair, the electromagnetic forces between the atoms of your body and the atoms of the surface beneath you, the same forces governed by the Pauli exclusion principle that prevent two electrons from occupying the same quantum state, and therefore prevent solid objects from passing through each other, those forces are shoving you off your natural spacetime path. The floor is constantly, continuously accelerating you upward, away from the geodesic you would otherwise follow. The sensation you interpret as weight, that pressing downward feeling, is not the earth pulling you, it is the floor pushing you. You are being pushed upward through curved spacetime, and your body registers the resistance to that push as weight. Gravity, in the Einsteinian picture, is not the thing making you feel heavy. The floor is making you feel heavy. The floor is the active agent. Gravity is the geometry. This is the first moment where most people stop and say, wait, that cannot be right. It feels like gravity is pulling me down. It does not feel like the floor is pushing me up. And that is a completely fair response, because phenomenologically, from inside the experience, the two are indistinguishable. Einstein knew this. He built an entire principle around it. But think about what happens when the floor is removed. When you step off a ledge, when you jump, when you are in an elevator whose cable has snapped, in those moments, the upward push stops. And what you feel, what every astronaut in orbit reports, what every skydiver reports in the first seconds before wind resistance builds, is not the sudden addition of a downward pull, it is the removal of an upward push. The sensation of weightlessness is not the absence of gravity. The sensation of weightlessness is the absence of the floor. Astronauts in the International Space Station are not outside Earth's gravity. The station orbits at an altitude of roughly 400 kilometers, about 248 miles, and at that altitude, Earth's gravitational influence is still about 90% of what you feel on the surface. They are absolutely within Earth's gravitational domain, but they are in freefall. The station and everyone inside it is constantly falling toward Earth in exactly the curve that takes them around it rather than into it. They are following their geodesic, their natural path through curved spacetime. And because nothing is pushing them off that path, because there is no floor accelerating them away from their free fall trajectory, they feel nothing, no weight, no down. Not because gravity is absent, but because they are finally free to follow it without interruption. This is the inversion that Einstein pulled off. Standing still is not the natural state. Free fall is. You feel your weight not because gravity is doing something to you, but because the ground is doing something to you. Right now, in this moment, you are being prevented from following your natural path through curved space-time by the electromagnetic stubbornness of the atoms in your chair. And the universe you thought you knew, stable, solid, anchored by a comfortable downward pull, is about to get considerably stranger. And here is the thread that ties all of this together, the one we will keep returning to throughout everything that follows. If gravity is not a force, if it is not a pull, if it is not even a thing that objects exert on each other in the usual sense, then what is it? What is the actual mechanism? What is space-time that it can be curved? And what does it mean that the most familiar phenomenon in your entire physical experience is, at its foundation, something that physics still cannot fully explain? We have replaced force with geometry. But we still do not know what geometry is made of. That question is where we are going. But we need to build the path there carefully, because the distance between your current intuition and the actual answer is longer than it looks. Let's talk about orbit, because orbit is one of those concepts that seems intuitive and is completely wrong in a way that matters enormously for understanding what gravity actually does. When most people picture a satellite in orbit, they picture something like this. The satellite is moving sideways very fast, and gravity is pulling it down, and the combination of moving sideways and being pulled down means it goes around in a circle rather than falling straight down. This is the textbook explanation. It is not wrong exactly, but it is Newtonian framing, and it hides something crucial, because in Einsteinian terms, the satellite is not being pulled at all. The satellite is in free fall. It is following its geodesic, its natural path through the curved spacetime that Earth's mass has created, and that natural path happens to loop around the Earth rather than intersect it. The satellite is not fighting gravity and not being saved from it. The satellite is doing exactly what an object does in curved spacetime when nothing interferes with it. It is following the curve. The distinction feels subtle until you push on it. In the Newtonian picture, you could ask, what would happen if we just turned off the sideways velocity? The satellite would fall straight down because gravity would pull it. But in the Einsteinian picture, the satellite in orbit and the satellite falling straight down are both following geodesics. They are both in free fall. The paths are different shapes because the initial conditions are different, but the mechanism is the same. There is no force acting on either of them. There is only curved space-time and objects following it. This matters because it undermines the intuition that there is something special about orbit, some balance between sideways motion and downward pull that creates this magical suspended state. There is no balance. There is no pull to balance against. There is only geometry and objects tracing paths through it. And here is the open question that the next part of our conversation is going to answer, or at least approach. If mass curves spacetime and curved spacetime creates the paths that objects follow, what does it actually mean for spacetime to be curved? What is curvature? What is being curved? And why does mass do the curving at all? That question is not one anyone has answered in a way that fully satisfies even the physicists asking it. But the journey toward it starts with what Einstein actually said, as opposed to what most people think he said, which turns out to be a subtly different thing with a dramatically different set of implications. Part 2. Gravity as curved reality, not force. Let's be precise about something, because precision here is the difference between understanding Einstein and just having a verbal shorthand that sounds like understanding. When people say Einstein showed that gravity is curved spacetime, they often mean something vague and metaphorical, like gravity sort of warps things, like there is a dent in a fabric and things roll into the dent and that is gravity. This is technically in the right neighborhood, but it is imprecise in ways that introduce exactly the wrong intuitions. So, let's say it carefully. What Einstein's general theory of relativity, published in 1915 after roughly 10 years of development, actually claims is this: the presence of mass and energy does not create a gravitational force field that acts on other masses. The presence of mass and energy changes the geometric structure of spacetime itself, and objects moving through that curved geometric structure follow the straightest possible paths available within that geometry. From the outside, those paths look like what we call gravitational attraction, but from the inside, from the perspective of the freely falling object, there is no force, there is no pull, there is only motion through geometry. This is not a small reframing. It is a complete replacement of the conceptual foundation. In Newtonian mechanics, spacetime is a fixed stage, absolute, flat, Euclidean, and gravity is something that happens on that stage, a force between objects. In Einsteinian mechanics, spacetime is not a stage. Spacetime is an active participant. Spacetime has geometry, and that geometry changes in response to what occupies it: mass and energy curve, spacetime. Curved spacetime tells mass and energy how to move. The physicist John Archibald Wheeler, who spent decades working on general relativity and who gave us the term black hole, summarized it as elegantly as anyone ever has. Mass tells spacetime how to curve, and spacetime tells mass how to move. That is the whole theory in one sentence, and it is both exactly right and also the beginning of a long series of questions about what, precisely, any of those words actually mean. Now, a crucial point that gets skipped over constantly: gravity affects time before it affects anything else. This is not a secondary feature of general relativity. This is central to it. The curvature that mass creates is not purely spatial. It is spacetime curvature, and the temporal component of that curvature is, for ordinary everyday gravitational fields like Earth's, actually larger than the spatial component. Clocks run slower in stronger gravitational fields. This is called gravitational time dilation, and it is not a hypothesis or a model prediction that might be confirmed someday. It is a measured, verified, daily use physical reality. The clocks aboard GPS satellites, orbiting at roughly 20,000 kilometers altitude, run faster than clocks on the ground, because they are higher up in Earth's gravitational field, and therefore experiencing less curvature. The difference is small, about 45 microseconds per day faster from the reduced gravity, offset by about 7 microseconds per day slower from the satellite's orbital velocity due to special relativity, giving a net correction of roughly 38 microseconds per day. Which sounds trivial, except that GPS navigation depends on timing signals accurate to nanoseconds, and 38 microseconds of daily drift would accumulate into positioning errors of roughly 11 kilometers per day if uncorrected. Your phone's GPS would be useless within hours if the engineers had not accounted for gravitational time dilation. We will come back to this in considerable detail, because it is one of the most concrete and undeniable demonstrations that spacetime curvature is not a metaphor. It is infrastructure. But let's stay with the curvature concept for a moment, because there is a very common visualization that helps in one way and misleads in another, and understanding where it misleads is important for getting to the actual picture. You have almost certainly seen the rubber sheet analogy. A stretched, flat sheet of rubber representing spacetime, and then a heavy ball placed in the center, causing the sheet to dent downward, and smaller balls rolling on the sheet, spiraling inward toward the dent. This is the classic representation of how mass curves spacetime and how other objects are drawn toward it. It is in countless science textbooks and documentary graphics, and it is problematic in several ways that matter if you actually want to understand what is going on. The first problem is the missing dimension. The rubber sheet is two-dimensional, representing the spatial dimensions of spacetime while leaving out time entirely. But, as we just established, the curvature of time is actually doing a lot of the work here, especially for the ordinary gravitational situations most relevant to human experience. A diagram that leaves out time is leaving out a significant portion of the mechanism. The second problem is deeper. The rubber sheet analogy requires you to already have gravity in order to understand gravity. The balls roll into the dent in the sheet because gravity, actual, external gravity, the kind you already understand, is pulling them downward. The sheet only works as a visual because there is a real gravitational field underneath it, causing the dents to act like slopes. This is, as physicists like to point out, a profoundly circular explanation. It uses gravity to explain gravity. The real curvature of spacetime is not a dent in some external, bigger, flat space that exists outside. There is no external space. The curvature is intrinsic. Spacetime is curved the way a sphere is curved, not by being dented into a surrounding space, but as a fundamental property of its own geometry. You can be on the surface of a sphere and determine that it is curved without ever leaving the surface, by measuring angles, by drawing lines and seeing if parallel lines eventually converge, by doing geometry and noticing that the results do not match what you would expect on a flat surface. The curvature of spacetime is like that. It is a property of the space itself, detectable from within, not requiring any external reference. The third problem with the rubber sheet is that it makes gravity look like a slope, like objects rolled downhill into a gravitational dent, the way a marble rolls to the low point of a bowl. And this captures something real. There is a sense in which things do move toward lower gravitational potential, but it builds entirely the wrong intuition about the mechanism. Because in general relativity, objects are not rolling downhill. They are following geodesics. And the concept of a geodesic is both simpler and more alien than a slope. A geodesic is the straightest possible path through a given geometry. On a flat surface, the straightest path between 2 points is a straight line. That is Euclidean geometry. On a curved surface, like the surface of the Earth, the straightest possible path is a great circle, the kind of arc that airplanes follow when they cross the ocean, curving around the globe rather than cutting a straight line across a flat map. The path is curved when you look at it on a flat map, but on the spherical surface itself, it is straight. It is the straightest thing available. That is a geodesic. In four-dimensional curved spacetime, objects follow geodesics. They follow the straightest possible paths through the curved geometry that mass and energy have created. They do not choose to do this. They do not accelerate toward the curve. They simply move, and moving in curved spacetime means the path curves in a way that, from our flat spacetime intuition perspective, looks like falling toward the massive object. An apple released from a tree is following a geodesic. A planet orbiting a star is following a geodesic. A photon bending around the sun is following a geodesic. None of them are being pushed or pulled. They are all doing the simplest possible thing, moving in a straight line through curved spacetime. This is the deep reversal that general relativity asks you to make. In the Newtonian picture, straight line motion is the default, and gravity is a force that curves the paths of objects away from straight lines. In the Einsteinian picture, following the local geometry is the default, and what we perceive as straight line motion, moving in a direction that feels to us like not gravitationally influenced, is actually a departure from the natural path. The natural path in curved spacetime is the curved one. Straight, in the everyday sense, requires active maintenance. Free fall is effortless. Why does any of this matter beyond being a more accurate conceptual picture? Because it forces a question that Newton never had to ask. Newton could describe gravity with extraordinary mathematical precision while leaving the mechanism entirely mysterious. He said, "I do not feign hypotheses." Einstein provided the mechanism. Mass curves, space-time, and objects follow that curvature. But Einstein's mechanism immediately raises a deeper question, one that sits at the center of everything that follows in our conversation. Why does mass curve spacetime? What is the actual mechanism by which the presence of energy changes the geometric structure of reality? Einstein's field equations tell you how much curvature a given distribution of mass and energy produces with breathtaking mathematical precision. They do not tell you why. The relationship is described perfectly. The reason for the relationship is not known. And here is where we find the same central mystery that has been following us since we started. Gravity has been redefined from a force to a geometry, from a pull to a path, from something that happens between objects to something that is a property of the space between objects. But that redefinition does not dissolve the mystery, it relocates it. Instead of asking why mass attracts mass, we now ask why mass warps geometry. And that question, as we will see, turns out to connect to the deepest unsolved problems in all of physics. Problems involving the very nature of space and time. Problems that general relativity itself breaks down trying to answer. But before we get to those breakdowns, let's stop and appreciate just how well general relativity works at the scales where it is valid. Because the reason physicists take curved spacetime seriously is not just theoretical elegance, it is engineering. It is technology. It is the fact that the equations make specific, quantitative predictions that have been tested and confirmed to extraordinary precision, in ways that affect your daily life right now, in ways that would fail spectacularly if the geometry were not real. And the most immediate, most personal, most inescapable example of this is sitting in your pocket, orbiting silently above your head, 24 hours a day, 7 days a week, precisely correcting for time dilation that a flat space-time universe would not produce. The satellites know space-time is curved. They have built that knowledge into the code that runs the system. And that fact, which we are about to examine in considerable detail, is one of the most concrete demonstrations available that the geometry of space-time is not a metaphor. It is the foundation on which modern civilization's navigation infrastructure rests. Part 3. The engineering proof that space is curved. There is a particular way that physicists and engineers sometimes describe the GPS navigation system that I find genuinely arresting, and it is this. GPS is a machine that only works because space-time is curved, not metaphorically, not approximately, not in the sense that it works better with relativistic corrections than without. In the sense that if you removed the relativistic corrections from the software entirely, if you just deleted that part of the code, the part that accounts for the geometry of space-time, the system would be providing wrong answers within hours, and the errors would grow at a rate of roughly 11 kilometers per day. 11 kilometers. That is not a rounding error. That is not a small imprecision that adds up over weeks. That is the difference between your navigation telling you to turn left on a specific street and telling you to turn left somewhere in a completely different neighborhood within a single day, and it would keep getting worse every day after that, drifting further and further from reality, compounding without bound. The GPS system, that everyday piece of infrastructure so ordinary that most people check it without thinking, that your phone uses automatically, that pilots and sailors and delivery drivers depend on without any awareness of what is happening in the background, is a continuous, real-time demonstration that the geometry of space-time is not a textbook abstraction. It is a physical reality precise enough to build global infrastructure on. It is a physical reality that your morning commute depends on. Let's be specific about what is actually happening up there, because the details matter and they are more interesting than the summary. The GPS constellation consists of at least 24 operational satellites, maintained by the United States military and operated by the Space Force, distributed across 6 orbital planes to ensure that at least 4 satellites are visible from any point on Earth's surface at any given time. They orbit at an altitude of roughly 20,200 kilometers, about 12,500 miles above the surface. Not in low Earth orbit like the International Space Station, which sits at roughly 400 kilometers, but much higher, in medium Earth orbit, completing roughly 2 full orbits of the Earth every single day. Each satellite carries multiple, extremely precise atomic clocks, typically cesium and rubidium clocks, accurate to within about 20 nanoseconds, which is 20 billionths of a second. Your phone determines its position by measuring the time it takes for signals from multiple satellites to reach it and triangulating from those arrival times. The math works because light travels at a known, constant speed, roughly 299,792,458 meters per second in vacuum, and so a difference in arrival time from 2 different satellites corresponds to a difference in distance, and enough of those distance measurements from enough satellites pins down your location on the surface. For this to work, the clocks on the satellites need to stay synchronized with the clocks on the ground, and they do not stay synchronized on their own. Because space-time curvature is real, and space-time curvature affects clocks, 2 separate relativistic effects act on those satellite clocks simultaneously, in opposite directions, and both of them come directly from Einstein's work. The first is gravitational time dilation, which is a consequence of general relativity, the theory of curved space-time. Clocks at higher altitudes, where Earth's gravitational field is weaker and space-time is therefore less curved, run faster than clocks at the surface. This is not an engineering imperfection. It is not a technical problem that better manufacturing could solve. It is a feature of the geometry of space-time itself. Time runs at a rate that depends on where you are in a gravitational field. The deeper you are in a gravitational well, the closer you are to the massive object creating the curvature, the slower your clock runs relative to a clock higher up. The satellite clocks, 20,000 kilometers above the ground, are significantly higher in Earth's gravitational well than your phone sitting in your pocket, and as a result of experiencing less space-time curvature, they run faster by about 45 microseconds per day, 45 millionths of a second every single day, accumulating. The second effect comes from special relativity, not general relativity. These are 2 different theories, both developed by Einstein, both describing different aspects of how space and time behave. Special relativity, published in 1905, deals with the relationship between space, time, and the speed of light for observers moving at different velocities. One of its central results is that moving clocks run slower than stationary ones. This is called time dilation due to velocity, and it is a consequence of the fact that the speed of light is the same for all observers, regardless of their motion. The GPS satellites are moving, orbiting at roughly 14,000 kilometers per hour, and that motion makes their clocks run slower relative to stationary ground clocks by about 7 microseconds per day. So the 2 effects act in opposite directions. Gravitational time dilation makes the clocks run fast, velocity time dilation makes them run slow, and the net result is that the satellite clocks run fast by about 38 microseconds per day relative to ground clocks. Now, 38 microseconds sounds like nothing. It is about 38 millionths of a second. In the course of a day filled with meetings and meals and sleep and everything else that fills human time, 38 microseconds is so small it might as well not exist. Your nervous system cannot register intervals that short. Your conscious experience has no access to that timescale, and yet, GPS navigation works by measuring how long it takes light to travel from satellite to your phone, and light travels at roughly 30 centimeters per nanosecond, about 1 foot per billionth of a second. 38 microseconds is 38,000 nanoseconds. Multiply 38,000 nanoseconds by 30 centimeters per nanosecond, and you get an accumulated positional error of about 11,400 meters per day, 11.4 kilometers. Every single day, growing every day. If the correction is not applied, within a week your GPS is off by 80 kilometers. Within a month, it is off by more than 300 kilometers. The system does not degrade gracefully. It fails completely and catastrophically in a way that cascades across every application that depends on it. The engineers who built the GPS system applied the correction. This was not an afterthought. The relativistic corrections were designed into the system from the beginning because the physicists and engineers working on it in the 1970s and 1980s knew the effects were real and knew they had to account for them. The atomic clocks aboard GPS satellites are actually pre-adjusted before launch. They are deliberately set to tick slightly slower than they would on the ground, so that once they are in orbit and the gravitational time dilation speeds them up, the two effects combine to produce a clock running at the right rate as seen from the ground. The correction is built into the hardware. It is not a software patch applied after the fact. It is not optional. It is not a refinement that improves accuracy slightly. It is the difference between a functional navigation system and a broken one. And the fact that it works, the fact that the specific numerical predictions of general relativity applied to a real engineering problem in the real world with real hardware produce results accurate enough to navigate a car down a specific street or guide an aircraft to a specific runway is one of the most powerful and most underappreciated demonstrations of physical reality that technology has ever produced. Think carefully about what that means. Every time your phone's navigation tells you where you are, it is doing so using equations that treat spacetime as a four-dimensional curved manifold, not as a flat Newtonian stage with a gravitational force field sitting on top of it, but as a geometrically warped structure where time itself runs at measurably different rates depending on your position within it. The hardware in orbit was designed around this. The clocks were calibrated around this. The software was written around this. The entire system, from the satellites to the ground stations to the receiver in your pocket, is predicated on the correctness of a theory that says gravity is not a force but the curvature of space-time. And that predication is tested continuously every single day by hundreds of millions of users whose navigation works correctly. GPS is the most continuously verified experiment in the history of physics, and it returns the same answer every time. Space-time is curved. The curvature affects the rate at which time passes, and the effect is exactly, not approximately, not roughly, but exactly what Einstein's equations predict. And this is not confined to GPS. The same physics runs through more of modern infrastructure than most people realize. The Galileo navigation system, operated by the European Union and consisting of 30 satellites in medium Earth orbit, applies the same relativistic corrections. The GLONASS system, operated by Russia, applies them. The Beidou system, operated by China, applies them. Every independent navigation constellation built by every spacefaring nation applies the same corrections derived from the same equations, because spacetime does not care which country's satellites are in it. The curvature is universal. The correction is non-negotiable regardless of national affiliation or political relationship. There is something almost poetic about the fact that American, European, Russian, and Chinese space programs all quietly agree on the geometry of space-time, even when they disagree on nearly everything else. Einstein's field equations are not subject to international negotiation. Financial infrastructure depends on it too, in ways that are less visible but equally real. The timing networks that synchronize global financial transactions, the kind that underpins stock exchanges, banking systems, and electronic payment infrastructure, require clock synchronization accurate to the nanosecond level. High-frequency trading systems execute transactions in microseconds, and the timestamps on those transactions need to be consistent across systems located in different parts of the world at different altitudes, moving at different velocities relative to each other. The relativistic corrections, applied to maintain that synchronization, are baked into the protocols. Every time a financial transaction completes, somewhere in the infrastructure chain, a relativistic correction is running. The global economy runs, in a small but non-trivial way, on general relativity. Data centers that synchronize their servers across continents use the same corrections. The Internet's timing infrastructure uses the same corrections. The modern technological world is, without most of its inhabitants being aware of it, a vast relativistic correction network operating continuously on top of curved spacetime, compensating for geometry that no one can directly perceive. And yet most people who use these systems every day, who check their navigation, tap their cards, scroll their feeds, have no idea they are living inside this correction network. The curvature is invisible to direct human perception. Your nervous system evolved to navigate a small slice of the physical world at walking speed and human scales, and it has no sensory apparatus for detecting 38 microseconds of daily clock drift, or the slight difference in gravitational potential between your head and your feet. The geometry is real, it is measurable, it is engineered around, but it is beneath the threshold of human experience, operating silently in the background of everything you do with technology. Now, GPS is in a particular sense a gentle demonstration of space-time curvature. Gentle because Earth's gravitational field is, by cosmic standards, relatively weak. The corrections involved are small in absolute terms, microseconds per day, not seconds or minutes. The engineering challenge is one of precision rather than encountering anything physically extreme or qualitatively different from everyday experience. GPS proves the curvature is real and consequential, but it does not show you the full drama of what curved spacetime can do when the geometry becomes truly intense. For that, you need to leave the gentle neighborhood of Earth's gravitational field and look at environments where the curvature is not a small correction to Newtonian physics, but the entire story, where the geometry is so extreme that space and time themselves are transformed into something that human intuition has no template for, something that the word gravity completely fails to capture. And in the search for those environments, the first thing that happened was not an observation of a distant extreme object. It was something far more immediate and far more dramatic. In September of 2015, for the first time in human history, we detected space-time itself moving. Not objects moving through space-time, not light bending around a curve in space-time. Space-time itself, the geometric structure of reality, oscillating, rippling, carrying energy across the universe the way a disturbance carries energy across the surface of water, except that what was rippling was not water and not any medium we have a name for. What was rippling was the geometry of space and time, the fabric, if you want to use that word, of reality itself. The detectors that caught this signal are called LIGO, the Laser Interferometer Gravitational Wave Observatory, and they operate at 2 sites simultaneously, one in Livingston, Louisiana, and one in Hanford, Washington, separated by about 3,000 kilometers. The separation is deliberate. A genuine gravitational wave signal will arrive at both sites at slightly different times, consistent with a wave traveling at the speed of light from a specific direction in the sky, while a local disturbance, a truck driving nearby, a minor seismic event, an equipment vibration, will only appear at one site. The coincidence requirement between the 2 detectors is the primary tool for distinguishing real signals from noise. The source of the September 2015 signal was a pair of black holes, each roughly 30 times the mass of the Sun, orbiting each other at an increasingly rapid rate as they spiraled inward due to the energy they were radiating as gravitational waves, until they collided and merged in a fraction of a second into a single black hole of about 60 solar masses. The remaining mass, roughly 3 solar masses worth of matter, was converted directly into gravitational wave energy in that fraction of a second. 3 times the mass of the Sun, converted to pure energy, radiated outward through spacetime as a ripple in geometry. The power output during that brief merger exceeded the combined luminosity of every star in the observable universe, every star, simultaneously. For a fraction of a second, this event occurred 1.3 billion light-years away. 1.3 billion years ago, when the most complex life on Earth was single-celled organisms, two black holes that had probably been orbiting each other for billions of years before that finally completed their merger. The gravitational wave from that event traveled across 1.3 billion light-years of expanding universe, passing through galaxies and galaxy clusters and the intergalactic void, spreading outward as a ripple in the geometry of space-time, losing amplitude as it expanded until it reached the two LIGO detectors in Louisiana and Washington and distorted the geometry of space-time at those locations by a distance of approximately 10 to the negative 18th meters, which is about 1/1000th the diameter of a proton. Let that number settle for a moment. 1/1000th of a proton diameter. A proton is already about 1 femtometer across, 10 to the negative 15th meters, which is itself 100,000 times smaller than an atom, which is itself too small to see with any optical microscope. And the gravitational wave distorted the detector by a factor of 1,000 smaller than that. This is not a measurement, this is a miracle of engineering. And LIGO detected it. The way LIGO works is conceptually simple. Even though the execution represents one of the most technically demanding achievements in the history of experimental science, a laser beam is split into two perpendicular paths, each travelling down a 4-kilometer-long evacuated tube, bouncing off a mirror at the far end and returning to a detector. Under normal conditions, the two beams travel exactly equal distances and return in perfect synchrony, producing a specific interference pattern when they recombine. If a gravitational wave passes through the detector, it stretches space-time along one axis while simultaneously compressing it along the perpendicular axis. This is the characteristic signature of a gravitational wave, alternating stretch and compression at 90 degrees to each other. When this happens, one tunnel becomes effectively slightly longer while the other becomes effectively slightly shorter, and the two beams no longer return in perfect synchrony, and the interference pattern shifts. By measuring how the interference pattern changes over time, LIGO can reconstruct the shape, frequency, and amplitude of the passing gravitational wave, and from those properties, infer the nature of the source. The scale analogy that I find most useful for conveying how extraordinary this measurement is goes like this. The distance from Earth to the nearest star system, Alpha Centauri, is roughly 4.2 light-years, or about 40 trillion kilometers. Imagine measuring that distance with enough precision to detect a change smaller than the width of a human hair. That ratio, hair width to 4 light-years, is approximately the ratio of the gravitational wave distortion to the length of the LIGO arms. That is the sensitivity LIGO operates at, routinely, every time it detects a signal. To achieve this, the mirrors must be isolated from every possible source of vibration, seismic noise, acoustic noise, thermal fluctuations in the mirror surfaces, the quantum uncertainty in the position of the mirror atoms themselves. The mirror suspensions are multi-stage pendulum systems that attenuate seismic vibrations by factors of billions across the relevant frequency range. The laser power is carefully controlled to reduce quantum shot noise. The mirrors are among the most perfectly polished optical surfaces ever manufactured, with surface irregularities measured in fractions of an atom diameter. The vacuum inside the tubes is one of the best vacuums ever achieved on Earth, better than the vacuum in low Earth orbit. Every possible source of noise has been identified, characterized, and suppressed to the absolute limits of current technology, and the signal is still barely above the noise floor. That is how small it is. And yet they found it. And then they found it again and again. As of the most recent observing runs, LIGO and its partner detectors, Virgo in Italy and CAGRA in Japan, have detected gravitational wave signals from dozens of merging compact objects, black hole pairs, neutron star pairs, and black hole neutron star pairs. Each detection is a separate confirmation of general relativity, a separate measurement of curved spacetime, doing exactly what Einstein's equations predict. The waveform shapes, the frequencies, the amplitudes, all of them match the theoretical predictions with the kind of precision that makes physicists genuinely emotional when they talk about it. Not because the emotional response is performed, but because matching a prediction to that level of accuracy for a theory published in 1915 from a source a billion light years away, using an instrument that measures subnuclear scale distortions in a 4-kilometer tube, that is the kind of thing that earns genuine awe. What gravitational wave detections confirm, beyond the immediate validation of the equations, is something more fundamental about the nature of spacetime. They confirm that spacetime is not a passive background. It is not the fixed, inert stage on which physics performs. It is a dynamic physical entity that carries energy, propagates disturbances, responds to the motion of massive objects, and participates actively in the physics happening within it. When two black holes merge a billion light-years away, the geometry of spacetime in this room, right now, where you are sitting, trembles, imperceptibly, unmeasurably, without instruments of extraordinary sophistication, but physically, genuinely. The geometry of the room you are in right now is not what it was a microsecond ago, because somewhere in the universe, something massive is moving. The trembling never stops. The universe is not quiet. This changes the conceptual picture of spacetime considerably. The rubber sheet analogy, which we already noted is misleading in several ways, treats spacetime as a passive medium that gets statically deformed by the presence of mass. But gravitational waves say spacetime is dynamic in a way that analogy cannot capture. Spacetime is more like the electromagnetic field than like a rubber sheet. It is a field that can carry waves, that stores and transmits energy, that has its own dynamics independent of the matter moving within it. When you accelerate a charged particle, it radiates electromagnetic waves, disturbances in the electromagnetic field that propagate outward at the speed of light. When you accelerate a massive object, it radiates gravitational waves, disturbances in the space-time field that propagate outward at the speed of light. The analogy is not perfect. Gravity and electromagnetism have important structural differences, but the key point is the same. Spacetime is not the background. Spacetime is the physics. It has degrees of freedom. It responds. It waves. And at the far extreme of spacetime dynamics, at the place where the equations stop producing useful answers and start returning infinities, we find the objects that represent the ultimate test of our understanding of curved spacetime. Objects where the curvature is not a small correction to flat space physics, not a measurable drift in atomic clocks, not a detectable ripple in a laser interferometer, but the complete and total replacement of everything intuition suggests about space, time, direction, escape, and existence. We find black holes. And black holes are where general relativity, the theory that has passed every test put to it for over a century, quietly admits that it is not the final word. A black hole is not a thing. This is the first adjustment the concept requires, and it is a significant one. A black hole is a region of space-time. Specifically, it is a region in which the curvature of space-time has become so extreme that the set of available geodesics, the natural, effortless paths through the geometry, all point inward. Not most of them, not the ones with insufficient velocity to escape. All of them, every possible trajectory through space-time in that region, including the trajectories that light follows, which are the maximum speed trajectories available in any space-time, curves inward and terminates. There is no outward direction available, not because an irresistible force is pulling everything in, but because the geometry itself has been warped to a configuration in which outward simply does not exist as a direction. The paths are all one way. Inward is the only option the geometry provides. The boundary of this region is called the event horizon, and it is perhaps the most conceptually strange object in all of physics. The event horizon is not a surface, it is not a wall, it is not a place where the physical properties of space change abruptly. If you were falling into a black hole of sufficient mass, you would cross the event horizon without feeling anything unusual. No barrier, no sensation, no warning signal. The event horizon is purely geometric. It is the boundary of the region from which no geodesic leads outward. Cross it, and the geometry of your available future paths has been restructured. Before the horizon, some geodesics lead outward and some lead inward, and with enough velocity, you can choose an outward one. After the horizon, every geodesic leads toward the singularity. The choice has been removed not by force, but by geometry. Your future has been geometrically redirected. In April of 2019, the Event Horizon Telescope collaboration released the first image of a black hole, or more precisely, the first image of the environment immediately surrounding a black hole's event horizon. The object imaged was the supermassive black hole at the center of the galaxy Messier 87, located about 55 million light-years from Earth, and containing a mass approximately 6.5 billion times the mass of the Sunday. 6.5 billion solar masses. To put that in scale, our entire solar system, from the Sun to the outermost edge of the Oort cloud, spans roughly 2 light-years. The event horizon of Messier 87's black hole has a diameter of roughly 38 billion kilometers, which is larger than the distance from the Sun to Neptune by a factor of about 2.5. It is enormous by solar system standards. It is by galactic standards a compact point. What the image shows is not the black hole itself. By definition, nothing escapes from within the event horizon, including light, so the black hole itself is invisible. What the image shows is the shadow of the black hole, the region of apparent darkness carved by the event horizon, surrounded by a ring of light produced by gas and plasma, falling into the black hole and being heated to temperatures of billions of degrees, glowing brilliantly across a range of frequencies, including the radio wavelengths the telescope array was designed to detect. The ring is not uniform. It is brighter on one side, because the gas on that side is moving toward us as it orbits, and the Doppler effect boosts its apparent brightness. The shadow is not perfectly sharp, because photons from behind the black hole bend around it, and some of them end up in stable orbits around the black hole for a time before escaping in our direction, creating a bright ring at the boundary of the shadow. Every feature of that image, the size of the shadow, the shape of the ring, the brightness asymmetry, is predicted by general relativity with quantitative precision. It is a photograph of a geometry. It is the shape of curved spacetime captured in light. And near the center of that geometry, at the point the mathematics calls the singularity, the equations return infinity, infinite density, infinite curvature. And in physics, infinity means the model has failed. It does not mean there is a point of literally infinite density at the center of every black hole. It means the theory being used to describe the situation is being pushed beyond its domain of validity into a regime where it is no longer a reliable guide to physical reality. General relativity, the theory that predicted gravitational waves with enough precision to match LIGO's measurements, that explained the GPS clock corrections to the nanosecond, that gave us the black hole image, returns infinity at the singularity. It breaks. And it breaks precisely where quantum effects should become important, at the scales of extreme density and extreme curvature, where the discrete, probabilistic nature of quantum mechanics can no longer be ignored. This is where the engineering proof of curved spacetime leads us inevitably to the boundary of what we know. GPS proves the curvature is real. Gravitational waves prove it is dynamic. black holes prove it is extreme, and the singularity proves it is incomplete. The geometry is real enough to build infrastructure on, real enough to detect across 1 billion light years, real enough to warp the paths of photons into rings around an object 55 million light years away. And it is still not the final answer. It is still a description in search of a deeper explanation. It is still, at its most extreme application, a framework that returns nonsense and politely admits it does not know what comes next. What comes next is the question that drives modern theoretical physics. What is spacetime actually made of? Why does mass curve it? Why does the geometry break down at singularities? And is spacetime itself the four-dimensional manifold that GPS satellites drift through, that gravitational waves ripple across, that black holes warp into geometric traps, actually fundamental? Or is it emergent from something deeper, something quantum, something that we have not yet found the language to describe? We have the engineering, we have the proof. Now comes the part where the proof opens into mystery. And the mystery, as we are about to see, goes considerably deeper than the geometry. Part 4. What is curvature made of? Here is a thought experiment that Einstein considered one of the most important insights he ever had, the one he called the happiest thought of his life, which is an interesting thing to say about an intellectual experience rather than a personal one, but that is the kind of person Einstein was. Most people, when asked about the happiest thought of their life, describe something involving other people, or a place, or a moment of unexpected beauty. Einstein described sitting in a chair in the patent office in Bern, Switzerland, in 1907, and suddenly realizing something about falling, which tells you something about Einstein, and also something about how extraordinary the realization actually was. Here is the thought experiment. Imagine you are in an elevator, not a normal elevator in a building, but a sealed elevator, with no windows, no exterior connection of any kind, floating somewhere in empty space, far from any massive object. You are weightless inside it. Everything floats. Nothing has a preferred direction. There is no up, no down, no sensation of gravity whatsoever. Now imagine that the elevator begins to accelerate. Some engine or rocket attached to the outside starts pushing it upward, and as it accelerates, the floor presses up against your feet. You feel weight. Objects placed on the floor stay there. A ball thrown horizontally curves downward toward the floor. Everything behaves exactly as it would if you were standing in a room on the surface of the earth. You feel heavy. There is a clear down direction. Physics feels normal. Now the question Einstein asked, is there any experiment you can perform from inside that sealed elevator with no access to any external reference that would tell you which situation you are actually in? Are you accelerating through empty space? Or are you stationary in a gravitational field? You cannot look outside. You cannot consult a GPS receiver. You can only do physics experiments with whatever equipment you have in the elevator. So you try pendulums, and they swing the same way in both cases. You try dropping objects, and they fall the same way in both cases. You try measuring the rate at which your clock runs relative to a clock on the floor, and the difference is the same in both cases. You try bending a light beam with a mirror arrangement, and it curves the same way in both cases. Every single physical measurement you can make returns identical results regardless of which situation you are actually in. The answer, according to general relativity, is that no experiment can distinguish them, not because we have not thought of the right experiment yet, not because our instruments are not sensitive enough, but because at the fundamental level, a gravitational field pointing downward and an upward acceleration of the same magnitude are not two different physical situations that happen to look similar. They are the same physical situation described from two different perspectives. This is the equivalence principle, and it is not a secondary feature of general relativity or a useful approximation or an interesting philosophical observation. It is the cornerstone of the entire theory. Einstein built general relativity on this foundation, and everything that came after, the field equations, the geodesic motion, the the curvature of space-time, the bending of light, gravitational time dilation, gravitational waves, black holes. All of it follows, ultimately, from taking the equivalence principle seriously as a fundamental statement about the nature of reality. What does it mean at the level of implications? It means that gravity, locally, is frame-dependent. It means that whether or not a gravitational field is present is not an absolute fact about the universe. It is a fact about your reference frame. An observer in free fall, with no surface beneath them to push against their natural geodesic path, experiences no gravitational field, none. The sensation of gravity has completely vanished, not because gravity has been switched off, but because the observer is following the geometry of space-time without interference. And following the geometry without interference is what it feels like to be in the absence of any force. Gravity, from inside a free-fall frame, is simply not there. It has been transformed away by a choice of perspective. And this has an immediate consequence that is worth sitting with carefully, because it inverts the intuition of almost everyone who has not thought about general relativity. If an observer in freefall experiences no gravity, then freefall is the inertial state. Freefall is the state of no force acting. A freely falling object is not being accelerated by gravity in any physically meaningful sense. It is moving inertially. It is moving the way objects move when nothing is pushing or pulling them through curved space-time, following its geodesic, doing the simplest possible thing. The object sitting on the ground, held stationary relative to the Earth's surface, is the one being subjected to a genuine force. The electromagnetic forces in the floor are pushing it away from its natural free-fall path, accelerating it upward through space-time, and the sensation of weight is the felt consequence of that acceleration. You can verify this right now if you have a smartphone. The accelerometer in your phone, the sensor that detects orientation and motion, reads approximately 9.8 meters per second squared when the phone is sitting still on a flat surface, not 0, 9.8 upward. The accelerometer is not broken. It is not measuring your motion through space because you are not moving through space. It is measuring the upward force that the table is exerting on the phone, the force that is preventing the phone from following its freefall geodesic. It is measuring the departure from freefall. It is measuring, in the most direct possible way, the thing that general relativity identifies as the actual physical event, the continuous acceleration away from the natural space-time path. When you pick the phone up and drop it, the accelerometer reads 0 during the fall, not 9.8, 0, because during freefall, nothing is pushing the phone. It is following its geodesic. It is in the inertial state. The accelerometer has nothing to measure. And the moment it hits the ground and something starts pushing it again, the reading jumps back to 9.8. This is not a philosophical interpretation. It is what the instrument reads. The instrument agrees with Einstein and disagrees with Newton, and it does so every single time you drop your phone, which, to be fair, is probably more often than any of us would prefer. Now, if gravity is equivalent to acceleration, and if gravity can be completely eliminated by choosing the freefall reference frame, then gravity is not a force in the same fundamental sense that the other known forces of nature are forces. And this distinction matters enormously, because it is the reason gravity has resisted every attempt to integrate it into the framework that successfully describes everything else. Consider the other forces. Electromagnetism, the force between charged particles mediated by photons, responsible for chemistry, light, electronics, and essentially all of the technology surrounding you right now, cannot be made to disappear by choosing a reference frame. If you are a positively charged particle sitting near another positively charged particle, you feel a repulsive force. If you accelerate, if you go into freefall, if you change your reference frame in any way allowed by physics, the force is still there. It has changed its mathematical description slightly, but it has not gone away. The same is true for the strong nuclear force, which binds quarks together inside protons and neutrons, and for the weak nuclear force, which governs certain types of radioactive decay. These forces are absolute in a way that gravity is not. Their presence or absence does not depend on your reference frame. They are frame-independent physical realities. Gravity is different. Gravity, as a locally experienced phenomenon, is frame-dependent. You can make it vanish by going into freefall. And this difference, this fundamental structural distinction between gravity and all the other forces, is exactly what makes gravity so stubbornly resistant to the theoretical framework that handles everything else with such extraordinary success. That framework is called quantum field theory, and it is arguably the most successful scientific framework ever developed. Quantum field theory describes the universe at small scales, at the level of elementary particles and their interactions, and it does so with a precision that is simply staggering. The prediction of the magnetic moment of the electron, which quantum field theory calculates from first principles, matches the experimentally measured value to 11 decimal places. 11. That is like predicting the distance from Earth to the Moon to within the width of a human hair. No other theoretical framework in the history of science comes close to that level of quantitative agreement with experiment. Quantum field theory describes forces as arising from the exchange of particles. The electromagnetic force between two electrons is, at the quantum level, mediated by the exchange of photons, particles of light. The electrons emit and absorb photons, and the momentum carried by those photons is what produces the apparent force between the electrons. Similarly, the strong nuclear force is mediated by gluons, and the weak nuclear force is mediated by the W and Z bosons. These force-carrying particles are called gauge bosons, and the framework of quantum field theory for describing them is called gauge theory. It is one of the most mathematically elegant structures in all of physics, and it works extraordinarily well for every force that has been tested within it. So the natural question, the obvious next step, is to ask, what is the gauge boson for gravity? What is the particle that mediates gravitational interactions the way photons mediate electromagnetic ones? The answer, theoretically, is the graviton, a massless particle with a spin quantum number of 2 compared to spin 1 for photons that would propagate gravitational interactions at the speed of light, and whose exchange between massive objects would produce the gravitational attraction we observe. The graviton is theoretically well defined. Its properties can be derived from the structure of the theory, and it has never been detected. Not because our particle detectors are not sensitive enough, though that is also true, but because, as we are about to see, the theory that predicts it breaks down in a way that suggests something is fundamentally wrong with the approach. When physicists attempt to calculate the probability of gravitational scattering events using standard quantum field theory techniques, the same techniques that work perfectly for electromagnetism, the answers come out infinite. Not approximately infinite, not very large, but mathematically infinite. And in physics, infinity in an answer means the calculation has failed. It means the theoretical framework is being applied beyond its domain of validity, into a regime where it no longer produces reliable results. The infinities that appear in quantum gravity calculations are not the manageable kind that appear in quantum electrodynamics and can be removed by a procedure called renormalization, a technically demanding but mathematically well-defined process that has been rigorously validated. The infinities in quantum gravity are non-renormalizable. They cannot be systematically removed. They proliferate without bound as you try to push the calculation to higher energies. The theory is, technically speaking, sick. It is not just incomplete. Its mathematical structure, at high energies, is pathological in a way that signals a fundamental problem with the approach rather than a technical hurdle to be overcome. This is the incompatibility at the heart of modern physics, and it is not a minor footnote or an obscure technical issue for specialists. It is a crack running through the entire foundation of the subject. General relativity, smooth, continuous, geometric, extraordinarily accurate at large scales, cannot be reconciled with quantum mechanics, discrete, probabilistic, field theoretic, extraordinarily accurate at small scales, using any of the tools currently available. They work in their respective domains. They fail when you try to make them work together. And there are physical situations, real physical situations that exist in the universe, not thought experiments, where both are required simultaneously. Black hole singularities. The first fractions of a second after the Big Bang. These are not exotic edge cases. They are the universe's way of telling us that our current theoretical structure is incomplete. The scale at which the incompatibility becomes critical has a name, the Planck scale. The Planck length is approximately 1.6 times 10 to the negative 35 meters. To put this in context, a proton is about 1 femtometer across, which is 10 to the negative 15 meters. The Planck length is 20 orders of magnitude smaller than a proton. It is 10 to the negative 20 power times the size of a proton. No instrument built by humans has come close to probing this scale directly. The most powerful particle accelerator ever built, the Large Hadron Collider at CERN, probes scales of roughly 10 to the negative 19 meters, still 16 orders of magnitude larger than the Planck length. We have no experimental data about what physics looks like at the Planck scale. We have theoretical arguments about what must happen there. Spacetime geometry must become quantum. The smooth manifold of general relativity must break down into something granular and uncertain, but no confirmed observations. We are theorizing about a regime we cannot reach with any instrument that currently exists or that we know how to build. Into this gap, several theoretical frameworks have been proposed, each with its own vision of what physics looks like at the Planck scale, and each with its own way of reconciling gravity with quantum mechanics. None of them are experimentally confirmed. All of them are, in various ways, mathematically impressive and physically speculative, and between them, they represent the current frontier of humanity's attempt to understand what gravity actually is at its most fundamental level. String theory is the most extensively developed of these frameworks, with a research community that has spent roughly 50 years building its mathematical structure. The central idea is a replacement of the foundational ontology of physics. Instead of point-like particles as the elementary constituents of matter and force, string theory proposes that the fundamental entities are one-dimensional objects, strings, that vibrate in different modes. Different vibrational patterns of the same string correspond to different particles. An electron is a string vibrating in one particular mode. A quark is a string vibrating in another mode. A photon is a string vibrating in yet another mode. And critically, a graviton, the quantum carrier of gravity, is also a string, vibrating in a specific mode characterized by the spin-2 property that the graviton must have. Gravity, in string theory, is not inserted by hand. It falls out automatically from the mathematics of vibrating strings. The theory does not choose to include gravity. It cannot avoid it. This is genuinely remarkable. Every previous attempt to build a consistent quantum field theory that included gravity had to put gravity in by hand and then found that it broke the mathematics. String theory builds a consistent quantum framework and finds gravity already there, as an unavoidable consequence of the string structure. This is widely considered one of the strongest arguments in string theory's favor, not the only argument, but a significant one. The theory also naturally unifies gravity with the other forces, in the sense that all particles and all forces emerge from the same underlying objects, vibrating in different ways. The cost is substantial, however. String theory requires additional spatial dimensions beyond the 3 we experience. The most consistent versions require 9 or 10 spatial dimensions, for a total of 10 or 11 spacetime dimensions. The extra dimensions are assumed to be compactified, curled up at scales too small to detect directly, but the mechanism of compactification introduces a vast landscape of possible solutions, estimated at something like 10 to the 500 power different possible configurations of the extra dimensions, each corresponding to a different set of physical laws and constants. String theory does not uniquely predict the physics of our universe. It predicts a nearly infinite number of possible universes, and we live in one of them, but the theory itself does not explain which one or why. This is the landscape problem, and it is a deep challenge to the predictive aspirations of the theory. A framework that can accommodate 10 to the 500 different physical realities has limited power to predict what any specific reality will look like. Loop quantum gravity approaches the problem from an entirely different direction, and the starting philosophy is almost the opposite of string theories. Where string theory extends the matter sector, replacing particles with strings, loop quantum gravity focuses directly on quantizing spacetime itself. The question it asks is, what happens if you apply the mathematical procedures of quantum mechanics directly to the geometry of spacetime rather than to the matter fields living on that geometry? What does a quantum version of curved spacetime look like? The answer loop quantum gravity proposes is that spacetime at the Planck scale is not smooth, it is granular. It has a minimum unit of area, approximately 10 to the negative 70 meters squared, and a minimum unit of volume, below which the concept of area or volume simply does not apply, in the same way that asking for a temperature below absolute zero does not apply. Spacetime, in this framework, is woven from a network of finite, discrete, interlocking loops of geometric information, the spin networks and spin foams of the mathematical formalism. What we experience as the smooth, continuous, four-dimensional manifold of general relativity is the large-scale, low-resolution limit of this discrete structure, the same way that water looks and behaves like a continuous fluid at human scales, even though it is actually made of discrete molecules that have nothing fluid about them individually. Zoom out far enough from the Planck scale granularity, and the smooth spacetime of general relativity emerges naturally. Zoom in to the Planck scale, and the smoothness dissolves into something grainy and discrete, something that the classical concept of a point in space does not apply to because points do not exist at that scale. Loop quantum gravity handles the singularity problem differently from string theory, and the difference is significant. In general relativity, the singularity at the center of a black hole and the singularity at the beginning of the universe, the Big Bang, are points where the theory breaks down, where density becomes infinite and the equations return nonsense. In loop quantum gravity, the minimum volume of spacetime prevents density from ever becoming truly infinite. When matter is compressed to the Planck density, the discrete structure of spacetime prevents further compression. The singularity is replaced by an extremely dense but finite quantum state, and the dynamics of the theory, working with the discrete quantum geometry rather than the smooth classical one, allow the physics to continue through what was previously the singularity. For the cosmological case, this suggests that the Big Bang was not the beginning of everything but a quantum bounce, a transition from a previous contracting phase of the universe, collapsing under its own gravity, that reached maximum density at the Planck scale and then rebounded into the expanding universe we observe. What we call the beginning might be a middle. Both string theory and loop quantum gravity have achieved significant theoretical successes, and both face significant unresolved challenges, the most pressing of which is the same for both. Neither has produced a unique, concrete, experimentally testable prediction that distinguishes it from its competitors, and that could, in principle, be confirmed or falsified by an experiment we can actually perform with current or near-future technology. This is the central challenge of quantum gravity research, and it is not merely a practical engineering problem of building better instruments. At the Planck scale, the energy required to probe the physics directly exceeds, by many orders of magnitude, anything a particle accelerator could plausibly achieve. We may never have direct experimental access to the Planck regime, which means quantum gravity theories may need to find confirmation through indirect effects, subtle imprints on cosmological observations, corrections to black hole thermodynamics, patterns in the cosmic microwave background, rather than through the kind of direct collision experiments that confirmed the standard model of particle physics. And then, sitting somewhat outside both of these frameworks, is a line of thinking that is in some ways the most radical of all, the idea that gravity is not fundamental. Not in the sense that it reduces to something more fundamental, the way chemical reactions reduce to atomic physics and atomic physics reduces to quantum electrodynamics, but in the sense that gravity is emergent, that it is not a basic feature of the universe at all, but a macroscopic consequence of more fundamental physics, in the same way that temperature and pressure are macroscopic consequences of molecular motion rather than fundamental features of reality. The physicist Erik Verlinde, working at the University of Amsterdam, published a paper in 2010 that proposed exactly this. In Verlinde's framework, gravity is an entropic force. It does not arise from a fundamental field. It does not have a gauge boson. It is not one of the basic interactions. It arises from the statistical tendency of systems to increase entropy, the same thermodynamic principle that explains why heat flows from hot objects to cold ones, why gases expand to fill containers, why you cannot unscramble an egg. In Verlinde's picture, the gravitational attraction between two masses is not fundamentally different from the osmotic pressure that drives water through a semi-permeable membrane toward higher solute concentration. Both are entropic effects. Both arise from the overwhelmingly probable direction of large-scale statistical behavior. Neither requires a fundamental force carrier. If gravity is entropic, then asking about the graviton is the wrong question. It is like asking about the carrier particle for temperature. Temperature does not have a carrier particle because temperature is not a fundamental interaction. It is an emergent statistical property of the average kinetic energy of a large number of molecules. Verlinde argues that gravity occupies the same conceptual category, not a fundamental interaction to be quantized, but an emergent thermodynamic effect to be derived from the statistical mechanics of whatever the fundamental degrees of freedom of spacetime actually are. This idea connects to one of the most tantalizing threads in modern theoretical physics, one that involves an unexpected relationship between gravity, spacetime geometry, and something that sounds entirely unrelated: information. Specifically, quantum information. The relationship was first hinted at in the work of Jacob Bekenstein and Stephen Hawking in the 1970s, when they discovered that black holes have thermodynamic properties, they have temperature, they have entropy, and that the entropy of a black hole is proportional not to the volume enclosed by the event horizon, but to the surface area of the event horizon. This was deeply puzzling. Entropy normally scales with volume. If you have a box of gas, doubling the volume roughly doubles the entropy. But black hole entropy scales with area, not volume. The information content of a black hole is encoded on its surface, not its interior. This observation eventually grew, through work by Gerard Hooft and Leonard Susskind, into the holographic principle, the general proposal that the maximum information content of any region of space is proportional to the area of its boundary surface, not its volume. The three-dimensional interior of a region is, in some sense, encoded on its two-dimensional boundary. The universe, in this framework, is holographic. The information needed to describe everything happening in a volume of space is contained in fewer dimensions than that volume occupies. The most mathematically precise realization of this idea is a result called the ADS CFT correspondence, published by Juan Maldacena in 1997 and widely considered one of the most important results in theoretical physics of the last 3 decades. AD-CFT establishes a precise mathematical equivalence between two completely different theories: a gravitational theory in a particular curved spacetime called anti-de Sitter space, and a quantum field theory without gravity living on the lower dimensional boundary of that spacetime. The two theories are dual. Every calculation in one corresponds to a calculation in the other, and the results are identical. Gravity in the bulk interior corresponds on the boundary to quantum entanglement, the quantum mechanical correlation between particles that Einstein famously called spooky action at a distance. Spacetime geometry in the interior is encoded in the pattern of quantum correlations on the boundary. The shape of space, the curvature of spacetime, the very existence of a geometric interior, all of it is, in this mathematical framework, a consequence of the entanglement structure of the boundary quantum field theory. The implication, if AD-CFT reflects something about physical reality rather than being merely a useful mathematical tool, is extraordinary. Spacetime is not fundamental. Spacetime is what quantum entanglement looks like when you stand far enough back. Gravity is not a force acting in space. Gravity is the geometric expression of quantum information structure. The reason mass curves spacetime is not that mass has some intrinsic connection to geometry. It is that mass represents a particular pattern of quantum information in the underlying degrees of freedom, and that pattern corresponds, at the level of the emergent geometric description, to curvature. If this is right, and it is important to say clearly that this is speculative, that it is not confirmed, that the AD-CFT correspondence has been established only in specific mathematical settings that may or may not correspond to the universe we actually live in, then the mystery of gravity has been relocated one more time. We went from Newton asking what the mechanism of gravitational attraction is, to Einstein answering with curved spacetime geometry, to the discovery that curved spacetime geometry cannot be quantized without breaking the mathematics, to the possibility that spacetime itself is emergent from quantum information. The mystery has not been solved, but the nature of the mystery has changed. The question is no longer what spacetime is made of, because if spacetime is emergent, that question is malformed. Asking what spacetime is made of is like asking what temperature is made of. Temperature is not made of anything. It is a property of the statistical behavior of things that are made of something. And if spacetime is in the same category, then the question is, what are those underlying things? What are the fundamental quantum degrees of freedom whose collective behavior at large scales and low energies looks like the smooth four-dimensional curved spacetime geometry of general relativity? We do not know. That is the honest answer. We have compelling mathematical structures, string theory, loop quantum gravity, the holographic framework, each of which captures some aspects of what a complete answer might look like, each of which resolves some problems while introducing others, none of which provides the full picture. We are in the position of someone who has correctly identified that water is not a fundamental substance, but has not yet found the atoms it is made of. The existence of the underlying structure is strongly suggested. Its nature remains to be discovered, and there is something genuinely humbling about this that I want to sit with for a moment before we move on. Gravity is the force, the phenomenon, the whatever it is that we have lived with the longest. That every human being who has ever existed has experienced every moment of every day, that we built physics around, that Newton quantified and Einstein geometrized, and that every particle physics experiment has to account for. It is the oldest subject in the history of natural philosophy, and it is the thing we understand least at the fundamental level. Every other force has been quantized. Every other force has a consistent quantum field theory that makes finite predictions. Gravity alone resists. Gravity alone refuses to fit the framework that describes everything else. The most familiar phenomenon is the most recalcitrant mystery, which suggests when you think about it carefully, that gravity is not actually familiar at all. The sensation is familiar. The effects are familiar. The equations describing those effects at human and astronomical scales are familiar and extraordinarily well confirmed. But gravity is a fundamental phenomenon, what it actually is, why mass curves spacetime, why the field equations take the specific mathematical form they take, whether spacetime is fundamental or emergent, whether the graviton exists, whether loop quantum gravity or string theory or something not yet invented will eventually provide the answer that is as open and as genuinely unknown as anything in science. The floor beneath you is pushing you upward through curved spacetime. We know that. We can calculate exactly how hard it is pushing, and we can verify the calculation to extraordinary decimal places. What we cannot tell you is what the curvature actually is, at the deepest level, what spacetime is, whether it is made of anything, or whether it is the shadow of something else, something quantum, something informational, something that our current language does not yet have the right words for. The happiest thought of Einstein's life opened a door. A century later, that door is still open, and what lies beyond it is still not fully in view, but we are closer than we have ever been. And the next step in the argument, the one that brings all of this back to the floor, back to the chair, back to the sensation of weight that started this entire conversation, is the strangest step of all. Part 5. The terrifying implications. Let's go back to the chair, or the floor, or wherever you are right now, whatever solid surface is in contact with your body, providing the sensation of stability, the experience of being somewhere, of occupying a position, of being in a state of rest. From the Einsteinian perspective, from the perspective that GPS satellites have confirmed, that gravitational wave detectors have confirmed, that every high-precision experiment ever designed to test general relativity has confirmed, you are not in a state of rest. You are being accelerated. Specifically, the surface beneath you is pressing against the atoms of your body, not through gravitational attraction, which in the GR framework is not a force at all, but through electromagnetic repulsion between electron clouds. The atoms of the floor and the atoms of your body cannot occupy the same space, a consequence of the Pauli exclusion principle, which prevents two fermions from sharing the same quantum state, and so they press against each other at the electromagnetic scale, and the result of that pressing is a net upward force transmitted through your body. That force, the normal force, the one that Newton would call simply the floor holding you up, is, in the GR picture, a genuine force. It is an actual acceleration. It is pushing you upward through space-time, off the geodesic you would naturally follow, preventing you from doing the effortless thing, which is free fall. The sensation of weight you feel right now is the sensation of being continuously deflected from your natural path. It is not the earth reaching up through the floor to pull you down. It is the floor pushing you up through the curvature of space-time and your body registering the departure from inertial motion. Every moment of your life that you have spent on the surface of a planet, you have been in a state of continuous forced deviation from your natural space-time trajectory. Free fall, genuine free fall, no floor, no contact, just you and the geometry, would feel weightless. It would feel like nothing, because nothing would be happening to you. You would simply be moving. It is worth sitting with that strangeness for a moment. Every skydiver who has leapt from an aircraft and described the sensation of falling as something utterly different from normal life, that liberating, stomach-dropping absence of weight, was not describing something poetic or metaphorical. They were describing, with visceral accuracy, what it actually feels like to be in an inertial state, to finally stop being pushed. The screaming wind, the rushing ground, the obvious danger, none of that changes the physical fact that the falling skydiver, in the instant before the parachute opens, is the freest they have ever been in a precise and technical sense. They are following a geodesic. The person standing safely on the tarmac, watching, is the one being subjected to a continuous force. Standing, sitting, lying in a bed, these are all active states. They require the continuous exertion of electromagnetic forces between atoms. They require the floor to be doing work. They require your bones and muscles and the structural materials of every surface you ever contact to be actively pushing you off the path that space-time is trying to put you on. The floor is working constantly. The building is working constantly. The whole engineering project of providing solid surfaces for humans to stand on is, at the deepest level, the project of continuously deflecting biological systems from their free-fall geodesics. Architecture is, in this sense, a collection of machines for preventing freefall. Every bridge, every foundation, every beam and column and load-bearing wall is a mechanism whose ultimate purpose is to keep matter from doing what space-time would have it do. Structures don't fight gravity, they fight the geometry, and the geometry, unlike an adversary with a will and a strategy, does not tire. This is not merely a conceptual reframing. It has a particular psychological weight, if you will excuse the terminology, because it inverts the intuitive sense of what is effortful and what is natural. You might have spent parts of your life working against gravity, climbing stairs, lifting weights, jumping. It feels like you are fighting the pull, exerting force against the downward direction. But in the GR picture, those activities are less different from standing still than they feel. Both climbing stairs and standing still involve the floor pushing you off your geodesic. Both are departures from freefall. The effortful state and the restful state are both, at bottom, the same kind of thing, constrained motion through curved space-time. The thing that would be truly effortless, truly restful in the deepest physical sense, is the one thing everyday experience never provides: genuine freefall. The astronaut floating in the ISS is not exerting effort to stay in that state. The astronaut is doing nothing, following the curve, tracing the geodesic. This is the natural state of matter in a gravitational field. Everything else is work. Now, take this picture and expand it outward. Think about what it means for the concept of down. Down is one of the most fundamental organizing concepts in human cognition. Languages, architecture, culture, physics, intuition, all organized partly around the axis defined by down. Down is where things fall. Down is where the ground is. Down is the direction gravity points. Down feels like an absolute direction, given by the universe itself, independent of perspective. But down, in the general relativistic picture, is not a feature of the universe. It is a local artifact of local geometry. Down on the surface of the Earth points toward the center of the Earth, because that is where the curvature of space-time is most intense, and geodesics near the Earth's surface curve toward that center. But there is no cosmic down. There is no universal floor. On the surface of the Moon, down points toward the Moon's center. On the surface of Jupiter, down points toward Jupiter's center. In open space, far from any mass, there is no down at all. Geodesics in flat space-time are straight lines, and none of them are privileged as the downward direction. Down is not in the universe. Down is in the local space-time geometry created by the nearest large mass, and it means whatever direction the local geodesics converge. This is unsettling in a particular way that is worth pausing on. You have a sense of down right now that feels absolute, completely unambiguous, the most obvious direction in your experiential universe. And that sense is real in the sense that it accurately describes your local geometry, the geometry shaped by the mass of the Earth you are sitting on. But it is not a feature of the universe. It is a feature of your location. Change your location by enough, get far from Earth, get close to a different mass, and down shifts. Get into freefall, and down disappears entirely. The concept itself is not fundamental. It is emergent from geometry, and geometry emerges from mass. And mass producing this geometric effect is, as we have established, still not fully understood. This should unsettle some ancient intellectual furniture. Philosophers argued for centuries about whether spatial directions were absolute properties of the universe, whether there was a real up and a real down baked into the fabric of existence, or whether they were merely relational, defined only by the positions of objects relative to one another. Newton, who was wrong about gravity but right about a great many other things, thought space was absolute. He thought there was a genuine sense in which the universe had fixed directions, a real grid. Einstein showed that even the shape of that grid depends on what is in it. Down is not the universe's instruction. Down is the universe's local suggestion, issued by the nearest concentration of mass energy, revised constantly as you move, and retracted entirely in the absence of matter. The most certain thing about your sensory world, the direction of the ground, turns out to be negotiable. Think about what this means for the ordinary experience of planetary motion. The planets orbit the Sun in their elliptical paths, and from the Newtonian perspective, the Sun's gravity is pulling them, holding them on these paths, keeping them from flying off into space. This is a natural and vivid way to think about it. But in the GR picture, the planets are not being held. They are not being pulled. They are following geodesics through the curved space-time that the Sun's mass has created, and those geodesics happen to be ellipses. There is no force holding Jupiter in its orbit. Jupiter is just doing the simplest possible thing in the geometry it finds itself in, following the curve. If you somehow removed the curvature, if the Sun's mass vanished instantaneously, though this is physically impossible, Jupiter would not gradually escape the Sun's pull. It would immediately cease to have any curved path available and would simply continue in a straight line through flat spacetime. The orbit is not maintained by an ongoing force. The orbit is the shape of a geodesic in curved spacetime. Consider what this means for Mercury specifically, and why Newton's gravity, which worked with extraordinary precision for every planet in the solar system, failed just slightly for the innermost one. Mercury's orbit precesses. Its ellipse slowly rotates over time. Newton's equations predicted most of that precession, accounting for the gravitational influence of all the other planets, but left a residual that could not be explained. For decades, astronomers searched for an undiscovered inner planet, something close enough to the Sun to nudge Mercury's path in the observed way. They even named it Vulcan. It was never found because it did not exist. What was found, eventually, was that Mercury's orbit dips close enough to the Sun that the curvature of spacetime there is intense enough to matter at observable scales. General relativity's prediction for Mercury's precession matched observation to extraordinary precision. Newton was not wrong in some vague sense. Newton was off by a specific amount at a specific location because Newton's model was an approximation of a deeper geometric truth, and Mercury's orbit lies where the approximation begins to show its edges. And this, extended to the largest scales, means that the universe is not holding itself together. It is not the case that galaxies orbit galactic centers because gravity is holding them, or that galaxy clusters hold together because of a gravitational pull. These are all geometries. Space-time is curved, and the motion of everything, every galaxy, every star, every photon, every atom, is the tracing of paths through that curved geometry. The universe is not held. The universe is shaped. Holding implies a force that could fail, a grip that could weaken. Shaping implies structure, and structure, once in place, does not need to be maintained by anything. The geometry is already there. The paths are already carved. The matter just follows them. And yet, as we have been building toward this entire time, we do not know what space-time is. We do not know why mass curves it. We do not know whether space-time is fundamental or emergent, smooth or discrete, the ultimate fabric or the shadow of something deeper. We can predict the curvature with extraordinary precision. We can engineer with it. We can build satellite systems that compensate for it, and detectors sensitive enough to feel it vibrate. But we cannot tell you what it is made of. We cannot tell you why the field equations have the specific mathematical form they have. We cannot tell you why the relationship between mass energy and geometric curvature is the one it is, rather than some other relationship. This is a peculiar position for a field of inquiry to be in. Physics in the 20th century scored victories so comprehensive and so precise that it became easy to mistake description for understanding. We have the Standard Model of particle physics, which describes with extraordinary accuracy the behavior of all known fundamental particles, and 3 of the 4 fundamental forces. We have general relativity, which describes the geometry of spacetime and the dynamics of gravity with a precision that modern technology can both exploit and test. Both of these theories work. Both of them produce numbers that match experiment to an almost embarrassing degree of accuracy, and they are incompatible with each other. General relativity treats spacetime as a smooth, continuous manifold. Quantum mechanics treats everything else as fundamentally granular, probabilistic, existing in superpositions until measured. When you try to apply the methods of quantum theory to gravity, when you try to quantize spacetime, the mathematics breaks down. You get infinities where you should get numbers. The 2 theories that represent our deepest knowledge of physical reality describe that reality in ways that are, at their foundations, mutually exclusive. And the place where they most urgently need to speak to each other, in the hearts of black holes, at the moment of the Big Bang, at the Planck scale, where quantum fluctuations of space-time geometry become significant, is precisely where neither of them individually can provide a coherent answer. Physicists have known about this incompatibility for nearly a century. It is not a new problem. It is not a problem that has gone unaddressed or that represents a failure of effort. The most talented mathematical minds in the history of the discipline have spent careers on it. String theory was developed, in part, as an attempt to bridge the gap, to provide a framework in which gravity and quantum mechanics could be simultaneously described. Loop quantum gravity was developed as an alternative approach, trying to quantize space-time itself without the added structure of strings and extra dimensions. There are other approaches: causal dynamical triangulations, causal set theory, the amplituhedron program, the holographic principle, and its descendants. None of them has yet produced a complete, testable, experimentally confirmed theory of quantum gravity. The gap remains. Everything in motion is in free fall in its own space-time context. You, sitting wherever you are in free fall, deflected by the floor. The moon is in free fall around the Earth. The Earth is in free fall around the Sunday. The Sun is in free fall around the galactic center. Everything is falling. Nothing is at rest. Rest does not exist as an absolute condition. What exists is geodesics, natural paths through curved geometry, and departures from geodesics enforced by contact forces. And every one of those contact forces, every piece of solid matter preventing every atom of biological life from following its geodesic, is temporary. Every flaw, every surface, every atom of matter that stands between you and freefall is the product of processes that will eventually end. Stars burn out, planets cool. In long enough time, the floor yields. In the longest possible view, the freefall is patient. The geodesic waits. This patience is not metaphorical. On timescales long enough to make the entire current age of the universe seem brief, even the most enduring material structures in existence will dissolve. Protons, if the grand unified theories that predict proton decay are correct, have a half-life orders of magnitude longer than the current age of the universe, but they do have a half-life. Stone, metal, the engineered materials that constitute every floor ever built by every civilization that has ever existed or will exist are temporary. The curve of space-time through which they divert you is, in a cosmic sense, far more durable than the matter that imposes the diversion. The geometry outlasts the floor. And when the floor is gone, matter returns to doing what space-time has always been asking of it. And here, at the end of this long unwinding of what gravity actually is, we arrive at the final, most genuinely unresolvable question. Not unresolvable because science is inadequate or because we have not tried. Unresolvable because we are asking something that no framework we currently possess can answer, and we know it. We can predict where every planet will be 1,000 years from now using general relativity. We can model the merger of black holes and predict exactly what signal LIGO will detect. We can calculate the time dilation aboard a GPS satellite to the precision required to navigate the surface of the Earth. We can do all of this with equations that are, within their domain of applicability, the most accurate mathematical description of physical reality ever written, and none of it tells us why. Why does space-time exist? Not how it behaves, why it exists. Why does the universe have a four-dimensional geometric structure rather than no structure? Why does the presence of energy change the shape of that structure? Why does the shape of that structure determine the paths that objects follow? Why do the field equations take the exact mathematical form they take, with this specific tensor structure, this specific relationship between the Einstein tensor and the stress-energy tensor? Why is the speed of light exactly the value it is, such that the relativistic effects we have been describing come in exactly the sizes they do? These are not questions that more experiments will answer. They are not even questions in the usual scientific sense, questions that point toward testable predictions that could confirm or deny a specific hypothesis. They are deeper than that. They are the questions you reach when you have peeled back every layer of mechanism and found, underneath, another mechanism, and peeled that back too, and eventually find yourself at a layer where there is no deeper mechanism available. Why does space-time exist? We do not know. We have no framework for even approaching an answer. We can describe the rules that space-time follows. We cannot tell you why those rules exist, rather than different ones, or rather than no rules at all. The gravity you have felt every day of your life is the surface of this mystery. It is the everyday manifestation of a geometric structure that has no known explanation for its existence and no known description at its most fundamental scale. It is the most familiar phenomenon in human experience and the least understood at the level of first principles. You feel it as weight, you feel it as down, you feel it as the comfortable solidity of a chair or a floor, but underneath that feeling is a four-dimensional curved manifold whose geometry is shaped by the energy of matter, whose curvature determines the trajectories of everything from photons to planets, whose fluctuations propagate as waves detectable only by instruments measuring changes 1,000 times smaller than a proton, and whose ultimate nature, whether it is fundamental or emergent, smooth or discrete, a thing or a description of things, remains the central, open question in theoretical physics. Newton gave you the equation. Einstein gave you the geometry. The geometry raised a question, and the question, 512 years after Copernicus began the process of relocating humanity from the center of the physical universe, is still unanswered. Not just unanswered in the sense of waiting for the next experiment, unanswered in the sense of not yet having a framework adequate to even formulate the question precisely. What is space-time? What is it made of? Why does it respond to energy by curving? Why does it exist at all? We can land spacecraft on comets. We can photograph black holes. We can build clocks accurate to 1 second in 300 million years. And we cannot answer the question of why the ground beneath your feet exists as something that can curve at all. We cannot answer the question of why falling feels like gravity rather than just being what things do when nothing stops them. We cannot answer the question of why the universe chose this geometric structure for itself rather than some other. Gravity is not a force pulling you downward. It is a manifestation of curved space-time geometry that replaces pull with motion through warped reality. That is what we know. That is what a century of experimental verification has established, beyond any serious doubt. But curved spacetime geometry is itself a description, not an explanation. And what spacetime actually is, what it is at its foundation, whether it is woven from quantum entanglement or quantized into Planck-scale loops, or emerges from some pre-geometric information structure we have not yet glimpsed, that question is the open frontier. That is where physics is alive, right now, uncertain and searching, and genuinely humbled by the depth of the thing it is trying to understand. There is a particular quality to this kind of not knowing that is worth naming because it is different from the ordinary kind. Most things we do not know because we have not yet looked carefully enough, or because the instruments are not yet sensitive enough, or because the right experiment has not yet been designed. That kind of ignorance has a clear remedy: more work, better tools, sharper questions. But the not knowing at the foundation of gravity is different in kind. We have extraordinarily sensitive instruments. We have the best mathematical tools our species has ever developed. We have dedicated generations of brilliant people to the problem, and we have not run out of brightness or effort. What we lack is not application. What we lack is the right conceptual vocabulary. We don't yet have the framework within which the question can even be properly posed. It is like trying to describe a color in a language that has no words for color, not because the language is impoverished, but because the category hasn't yet been discovered. The chair you are sitting on is actively working against the universe. It is pushing you off the path that spacetime is trying to put you on. And neither you, the chair, nor anyone who designed it understands, at the deepest level, what spacetime is, or why the chair's resistance to it feels, to your nervous system, like weight. You are being accelerated upward through curved reality right now, at this moment, and you will be for every moment you remain in contact with the surface of this planet. You have been your entire life. You will be until you are not. And the geometry shaping that experience, the four-dimensional manifold of spacetime curved by the mass of the Earth, tracing your path through a universe you will never fully see from inside, does not care whether you understand it. It does not need your comprehension to work. It worked for 13.8 billion years before you arrived, and it will continue for an interval so vast that our species' entire existence will eventually register as a brief fluctuation in the temperature of a cooling universe. The force you believed in your entire life is not there. What is there is stranger and older and deeper than anything the word force could ever contain. And we are standing, right now, at the very edge of understanding it, peering into the gap between general relativity and quantum mechanics, between geometry and information, between the physics we have and the physics we need, and finding that the gap is not narrowing as fast as we would like, because the question is hard, because the universe does not organize itself around human intuition, because reality at its foundation level is not required to make sense in terms available to primates who evolved to throw spears and recognize predators. But we are asking the question. That matters. The fact that a species of terrestrial animals has developed abstract mathematics powerful enough to detect space-time ripples from colliding black holes a billion light-years away, that is extraordinary. The fact that the same species cannot yet answer why space-time exists in the first place, that is humbling in the best possible way. It means there is more. It means the universe is larger than our current language for it. It means the story is not finished. The history of physics is, at its most honest, a history of successive humiliations. Every time we thought we had reached the bottom of things, every time we had a framework elegant enough, comprehensive enough, successful enough to feel like the final word, the universe produced a deeper layer. Classical mechanics gave way to electrodynamics, which gave way to relativity and quantum theory, which gave way to quantum field theory, which continues to yield phenomena that no single coherent framework has yet brought together. Each of these transitions was not merely an addition to knowledge. Each was a reorganization of the conceptual ground beneath the previous knowledge. What looked like the foundation turned out to be a floor above a deeper foundation, and there is no guarantee yet that the process terminates. There is no reason, in principle, why there must be a bottom layer, a final theory, a set of axioms from which everything else can be derived without remainder. Which means that when you feel the familiar weight of your body pressing into your chair, you may be feeling the surface of something without a bottom, a chain of explanation that does not end, a question that cannot, even in principle, be finally closed. Gravity has been, throughout all of human history, the most intimate physical relationship between our bodies and the universe. We have lived inside it, moved through it, been shaped by it, built civilizations in response to it, and it turns out we have been misreading it since the beginning. Not entirely, the effects are real, the predictions are accurate, the engineering works. But the story we told ourselves about what gravity is, about the nature of down, about the meaning of weight, about what is happening in the moment between leaving a surface and hitting another one, that story was incomplete in ways that matter deeply. The truth is both simpler and more alien. You are in a universe with a geometric structure. That structure curves in response to energy. You are a concentration of energy, and you curve space-time around yourself, slightly, in proportion to your mass. Every other mass curves it around itself, and the curvature of each determines the paths available to every other, and those paths are traced continuously by everything, everywhere, always, without force, without pull, without any mechanism that you can feel from inside the experience of following a geodesic. The floor is the anomaly. The falling is the default. The weight you feel is the universe pushing back against your attempt to do what comes naturally to matter in a gravitational field, which is to follow the curve, to trace the path, to move the way the geometry says to move. You are moving right now through the four-dimensional geometry of space-time, on a path shaped by a massive planet beneath you, in a solar system traced around a medium-weight star, in a galaxy among hundreds of billions, in a universe whose geometry we are only beginning to understand, whose curvature we can measure but not explain, whose existence we can describe in equations of extraordinary precision but cannot justify from first principles, and whose deepest nature, what space-time actually is, why it exists, what it is ultimately made of, remains the most important unanswered question in all of science. If gravity is not a force, then standing still was never still at all, and the floor is pushing you up through all of it, every single second. Welcome to gravity, the real kind.